Thanks a lot, Jeff. Yeah, so a slight change in direction for this talk here. I'm going to talk about underground storage of hydrogen focused on the Taranaki region of New Zealand. I'm giving this talk on behalf of a few other colleagues from Canterbury University and Auckland. Unlike some of the previous speakers, we've only been going on this topic for about 18 months. So about 5 years after Jeff thought he might quit hydrogen, we were just starting. So fairly slow off the mark. This topic is kind of like most of the topics that have been discussed over the last couple of days, is a fairly hot topic at the moment, particularly in the international literature. There's a lot going on, and we're kind of trying to tap into that to some extent. In terms of New Zealand rocks, just a bit of a flavour of what I'm going to say. Commercially, underground storage of hydrogen has only really been achieved in salt caverns. We don't have any salt rocks in New Zealand, so that's not a possibility here. So we won't really be considering that. That's kind of pushed us in the direction of looking at whether it's possible to store hydrogen in essentially hard rocks. The kind of conclusion that I want you to take away here is that from what we can see so far, it is possible, but quite a lot more work needs to be done before we can actually move towards any form of commercialization. So in the talk today, I'm going to just give you a brief overview of what is underground storage of hydrogen. We'll talk about why we should even bother thinking about it. And then I'll give you an overview of what we've done so far, some results, some opportunities, risks, and a bit of future work. Many of you may be aware that essentially there are two primary options in terms of storing hydrogen underground. You can stick it in anthropogenic caves or abandoned mines, for example, and that's essentially what's being done with the salt caves. Obviously, that requires some degree of some excavation, and particularly in hard rocks, it also requires some mechanism to ensure that the walls of the cave are sealed. So it's a fairly high cost exercise, and the amount that you can store is significantly less than what you could store in porous media storage systems. What I'd like to focus on today, so we're not really going to talk too much about the anthropogenic caves. That's an option that's kind of out there, but we haven't really investigated to any great degree. What we're going to talk about today is the porous media storage. And I just want to quickly talk a little bit about essentially what that is. So if we consider gas and oil systems in New Zealand, essentially what you require to hold the material underground is you need a seal layer, so a low permeability seal layer, overlying a porous and higher permeability reservoir rock, and in most cases this is a sandstone, so essentially grains of sand, hopefully mostly quartz, with pore space in between the grains, and that's the pore space that we hope to utilize for the storage system. In addition to that, you need some form of trapping mechanism, so some mechanism of holding the gas in position, and the most common trapping mechanism, particularly in Taranaki, but also worldwide, is essentially a domal system. So just think of a mixing bowl or a bucket turned upside down, and essentially most gases are relatively light. They tend to rise to the high point in the structure, and if you've got a good seal over the top of the reservoir, then those gases are held in place, and you can rely on them being where you put them or where you would hope they would be. So that's kind of a very quick summary of the system itself. Usually in those sorts of systems, as we've illustrated here, you have injection wells or withdrawal wells, which are in the top of the structure. If we look at that in a little more detail, there are quite a few elements that we need to fall into place to have an operational subsurface or underground hydrogen storage system. Clearly, we need a cap rock or a seal rock that maintains its integrity. So we don't want any diffusion through the rock. We don't want pressures to rise to the point where we would fracture the rock. And we don't want the rock itself, the cap rock, to have too many pre-existing fractures in it, because those can actually promote leakage of the gas out of the reservoir and into the overlying material. In addition to that, another biggie here is that we want the reservoir and seal rock to be relatively non-reactive, a bit like some of the speakers yesterday. We certainly don't want dissolution of material or deposition or precipitation of material. That's not ideal for sure. And that's kind of one of the biggest concerns about storing hydrogen in porous rocks. How the rock's going to interact with the hydrogen and what response is going to occur. I'm not going to talk too much about it here, but there's also some discussion in the literature about microbiological activity. It's something that needs to be considered. Organisms like to consume hydrogen in some cases, particularly in certain pressure and temperature regimes, and we need to understand that a little better than we actually do at the moment. Another key aspect of underground storage of hydrogen is ensuring that you have the injectivity and production to get the hydrogen into the ground and get it out of the ground when you want it. And coupled with the previous comment around reactivity, you want it to come out of the ground in a relatively pure state, not too contaminated by material which has been removed from the reservoir. I'm not going to talk too much about cushion gas here, but another requirement of these hydrogen storage systems is that you have cushion gas, which essentially sits under the hydrogen material and holds it in place, keeps the reservoir pressures high enough so that extraction is possible. There are all sorts of details around the cushion gas, which I'm not going to discuss here. The cushion gas does not need to be hydrogen. In fact, some studies suggested that methane cushion gas might give a better recovery rate than hydrogen itself. So that's kind of the basic system that I'm talking about here. Why would we bother with underground storage of hydrogen? Here's some numbers that we've taken from the literature. You may have different numbers, I'm not sure. They're ballpark numbers anyway. Essentially, the suggestion is that possibly about 10% of the global energy system will be taken up by hydrogen in the 20 years' time. If we look at the current New Zealand energy demand, that's about 72 petajoules. And the suggestion is that we may need to have capacity to store maybe 7 to 18 petajoules in New Zealand. Key thing here is that this is not going to be something that's required tomorrow. We're talking tens of years down the track. It's clear that in the intermediate time periods, smaller storage options may be more favorable. The ideal situation is to have storage that allows you to take advantage of intermittent renewable surplus energy at low cost and to essentially smooth out some of those highs and lows in the energy demand system. Also good to have some strategic reserve. The issue is that if we look at those numbers, we can store that amount of hydrogen above ground in cryogenic tanks and potentially also in the near surface and vertical shafts, but we're talking about having many hundreds of these storage containers, again at relatively high cost. If we compare that to the porous media options, it's likely that that we may only need a few of these to satisfy our national requirements. So I guess the thing here is that if we intend to store hydrogen and we want to store significant volumes of hydrogen, porous media is certainly an option that we need to consider. If we look at the graph on the right-hand side, essentially that's giving us you can see the hydrogen H2 box there in the upper right. that's essentially showing that it's giving us the option to store quite large power capacity where we require discharge durations of days, weeks, or months. So it's not something that you can that can provide you with immediate energy, but it's certainly something if we need to have long-term storage capacity. So what have we been doing? As I said, we've only been working for 18 months or so. As I also mentioned, there have been no underground hydrogen storage studies done in New Zealand. We have no salt rocks, and so we really need to start looking at the New Zealand system in that respect. Essentially what we've done is we've gone through both the New Zealand literature, mostly derived from the oil and gas industry, and the international literature to understand the requirements of underground hydrogen storage. We focused ourselves on the porous rock storage systems, and particularly we focused ourselves on depleted oil and gas fields, but we've also considered saline aquifer systems, which don't have the same demonstrated I guess containment, but they do have other advantages, first being that they can be closer to the surface. We've also done a few preliminary calculations with reservoir models, and we've looked a little bit at what we might do next. Apologies to probably most of the audience, we have not looked at any societal factors, we haven't looked at the economics, we haven't considered any of the engineering aspects of this particular study. So if I just quickly go through some of the results, the bottom line here is that we have operating oil and gas geological systems in Taranaki. These demonstrate that, at least for oil and gas, we have containment, we have reservoirs, we have cap rocks, and I think that's not a bad place to start. On this map here on the right, we can see all the fields that have been operating or are now depleted. There's quite a few of them. A lot of them are relatively simple anticlines. So again, think of that bucket turned upside down at relatively shallow depths. So they could be amenable to storage of hydrogen in the subsurface. A lot of the reservoir rocks are quite thick sandstone units, and they have quite good permeability, so they would be amenable to underground storage of hydrogen. We've gone through a preliminary site or field analysis, and there are at least 4 or 5 of the fields that are outlined here that look prospective for underground hydrogen storage. There are quite a number that don't look prospective. In particular, we've at this stage discounted fields that are offshore, and we're not particularly keen on the limestone reservoirs either, mostly because of their reactivity. Won't talk too much more about that. If we look at the hydrogen rock reactivity, we've looked through quite a lot of the existing well and rock information. Basically here, you don't want material that's going to be overly reactive. So rocks containing sulfates, carbonates, and pyrite are considered a bit of a tall order in terms of storing hydrogen. At least for the systems we've looked at, there are not substantial amounts of carbonate or pyrite reported. And so that's probably a good start. The issue is that you probably need to make sure that you've done a bit more digging into the actual rocks themselves, because even small amounts of carbonate and pyrite, particularly close to injection or extraction wells, may be problematic. So the more work's required there. We haven't looked in detail, as I said, at the microbiological activity. Again, that's very dependent on temperature, pH, pressure, and chemistry, but that's clearly something that needs a bit more of a closer look. In terms of the reservoir modelling, we've been fairly selective here. We've looked at just a few reservoirs, 3 depleted oil and gas fields and 1 sand unit, which is above one of the fields. Essentially, we've just used information from the literature. The models are as simple as we can possibly make them. So just a bit of a health warning here. Usually what happens is when you start off with simple models, you end up with what are close to best case scenarios. And as you understand more of the reservoir systems, things like capacity and injectivity tend to decrease. So having said that, some of the results. So essentially, as I mentioned before, at least some of the fields we've looked at, they have the potential at the moment, based on the simple modelling, to store a significant amount of our projected hydrogen storage requirements. So at least 30% of the requirements. Again, remembering that our models are quite simple and are likely to become much more complicated. In addition to that, the models suggest that we can inject and extract hydrogen at rates which are reasonable. They are less than what is currently achieved at the Aharoa gas field, for example, where we're storing gas. And that's clearly an area that we'll need to do a bit more work. That's critical. If we can't inject or extract gas, the hydrogen at high enough rates, then that becomes problematic. Having said that, of course, you always have the solution of sticking in more wells. The problem with that is that it's a balancing act between number of wells and economics. In terms of the storage systems themselves, as I said, the key here is how many wells are you willing to stick into the system, and how much is that all going to cost? Again, the summary here is that based on the modelling we've done at the moment, some of the reservoirs look quite prospective. They look like they're going to hold, they could hold significant quantities of hydrogen in the subsurface. They look like it should be possible to extract and inject hydrogen at reasonable rates. So what are the opportunities and the risks here? Clearly, one of the big opportunities for us is that we have had quite a number of operating oil and gas reservoirs, which means that we've got an enormous amount of data on hand. Our understanding of the rocks in Taranaki is probably an order of magnitude better than anywhere else in the country. And that means that potentially we have less investment to make before we can get to the point where we can make decisions about what's possible and what's not. Also in Taranaki, we've got quite a bit of existing infrastructure. I realise that there's some debate about to what extent we'll be able to use that, but it's possible that we may be able to use mixed systems, so gas and methane, for example, at least initially, and that may help us use some of that existing infrastructure. The other thing is that there's quite a bit of interest in underground hydrogen storage at the moment, and there's quite a lot of research going on, and we're in a good shape to kind of plug into that at this stage. Clearly, the big risks are that it's a new technology. There are no commercial porous media systems operating, certainly not in New Zealand, and neither globally either, so we've got a lot to learn. In New Zealand, I think there's quite a bit of uncertainty around how the reservoir and seals are going to respond to hydrogen injection. And it's quite clear that we're going to need to do quite a lot of site-specific modelling and investigation. So that brings us to the future work. Not sure how the time's going. Essentially, we really need to ask ourselves some key questions here around how much we might want to store, where we'd like to store it, and what sort of timeframes we want those actions to happen. Quick summary here is that if we're going to go down this track, we need to do quite a bit more work and really hammer some of the kind of fairly vague statements I've made in this presentation. I don't think there's any way of avoiding having to collect more data and undertake more modelling. And if we do this, we're kind of looking at development timescales of probably at least 5 to 10 years. So to conclude, there's a lot of work going on internationally in this space. The international literature is generally upbeat about underground storage of hydrogen. There's quite a few opportunities in Taranaki for potential storage in particularly depleted oil and gas reservoirs, but we do need to understand the systems a bit better, and particularly the chemistry and the injectivity. If we went down this track, the depleted oil and gas reservoir systems have the potential to store significant amounts of New Zealand's hydrogen storage requirements. Great, thank you very much.
Thanks very much, Andy. That was fantastic. Really enjoyed it. We've got time for one question. If someone from the audience has a question.
Can I leap in, Jeff?
Yeah, you can, Chris. I knew you'd be coming on this one.
Hi, Andy. Thanks. It's great to see somebody in New Zealand working in this area, because I think it's really important to a number of systemic systems. The question I've got really is about charging these things in the first place. How long is it going to take to charge a well, and how much is it going to cost in terms of just amount of dollars of hydrogen that we've generated and then stuck straight under the ground in order to get it back again? And is that something you've taken into account when you've been declaring what is too big or too small?
No, as I said, yeah, that's a great question. And I'm going to kick for touch here. We didn't look at the economics at all, but that's clearly a big issue, both in terms of where you site these things and what the infrastructure requirements are. And we did talk about the cushion gas, and I kind of glossed over that a little bit, but it's quite clear we're going to need a fair amount of cushion gas in there to make this going proposition as well.
Cool. Just as a rough number, what sort of period do you think it will take to charge one of the wells you've looked at so far? How long? A year? 2 years? 5 years? 10 years?
That's a good question. I would say it's going to be in the months to year time frame. It depends how big it is. It depends on the properties of the rock. So it's certainly, I guess, not an issue, but certainly something we need to consider. When we're looking at these systems, they really are longer term storage options. We can't expect to take significant quantities of hydrogen out of the ground kind of at the click of the finger. It's days to weeks to months to get significant quantities out of the ground.
That's really good.
Right,
my question is, I don't know much about this underground hydrogen storage, but if you put in pure hydrogen, does there need to be purification when the hydrogen comes back out? That's
another great question. There are two issues here, or two things that are worth considering. Firstly is a lot of these reservoirs have already got residual fluids and gas in them. So the question is, to what extent does that contaminate the material? And secondly, the reactivity of the rocks is quite critical in this respect. I mentioned pyrite and carbonate, but certainly if you were injecting into those types of materials, then you would have a lot of purification. And I think that the acid really comes on there to actually select a site which has fairly non-reactive rocks to avoid having the purification issues that you talked about.
We need to find a big diamond cavity.
I may just add something. We are, it's Peter from GNS Science from Taranaki, Taupo. We are currently looking into developing tools to do water rock and gases interactions at high temperatures and pressures. So maybe when we get there, we could see what we can do with the Taranaki rocks and see what's going on there.
Great, sounds fantastic.
Yeah, thanks again, Andy. That was a wonderful talk, and yeah, we really appreciate the work you're doing there.
Thank you.
Great.